last week. So we were looking at what we call the advection dispersion equation, which is given here. And so what this refers to is the transport of a component in a 1D porous medium, and right now we're just talking about single phase flow. And this is the accumulation with time of the concentration. This is the advection term. You can easily tell that because you've got a velocity there. And this is the dispersive term, and you've got dispersion there. And this is a partial differential equation. It depends on time and space x. And what we're seeking is a solution of that, so we know what the concentration of our component is at any time and any location. We often present this in dimensionless form, so we introduce the dimensionless concentration in this way, where C init is the initial concentration in the porous medium, and C Ing is the injected concentration. XD is the dimensionless distance, TD is the dimensionless time, and Peclet is this ratio of advection to dispersion. So if the Peclet number is very large, then advection dominates. In fact, you can ignore this term altogether. If Peclet number is moderate or low, then dispersion is large, and you need to keep that term. This results in a dimensionless partial differential equation, which we write like this. Again, if the Peclet number is really large, then 1 over a large number is small, and then you can neglect it. And we have some initial and boundary conditions. So the initial condition is that the dimensionless concentration is 0, and then we inject a dimensionless concentration of 1, and then if you go very far away, then the concentration would be 0. Sort of an odd boundary condition because it's a finite length porous medium, but we're defining this boundary condition as if it were an infinite or semi-infinite domain. Maybe I'll talk more about this later, but generally in reservoirs we have high Peclet numbers. So there are cases where we can neglect this altogether. At least, at minimum, we have moderate Peclet numbers, 10 or 100. And so you almost never see a case where advection can be neglected, not in our applications. But there are cases where you have to include both. So what we learned last time is that the dimensionless concentration as a function of space and time is given as here. So it's approximately equal to 1/2 the complementary error function, EFRC, of the position XD minus the time TD divided by 2 over the square root of TD times the Peclet number. I say approximate because there is an additional term that you would need to include, but it's almost always negligible, at least for moderate to high Peclet numbers. As I mentioned, those are the cases we care about. This complementary error function is just 1 minus the error function. So I could have rewritten that as 1 minus ERF, or the error function of that same argument there. Okay. I do have a detailed derivation of that in the appendix slides if you're interested. I'm not going to require you to know how to do that. You can solve this using Laplace transforms, and well, there's a few different ways you can solve the problem there. So, okay, this looks a little bit complicated, right? So we've got this error function, and most of you are not familiar with that. You haven't had it in any classes. But you are familiar with the exponential integral function that we learned in Reservoir 1, and it's sort of analogous to that in some ways. The error function is just a function. You know, you can, if you go into Microsoft Excel or Python or MATLAB or even Google it, might even be, you know, many calculators can do it. If you ask what the error function of some value is, it'll give you a number. It's defined as this integral, 2 over the square root of pi, 0 to, you know, I change my, yeah, sometimes it's a good idea to put a different variable there than the integral, but it's basically the integral of e to the minus some variable squared dt in that derivative. And you cannot analytically take the integral of e to the minus t squared. So none of the tricks you learned in calculus, integration by parts, none of those methods work for this. So there is no analytical solution. You have to use numerical solutions like the trapezoidal rule. Fortunately, that's tabulated for us, right? Or it's in calculators and software and stuff like that. So we don't need to worry about actually doing the integral. But the error function looks like this. And if you go to very small values of x, you get like, as you approach minus infinity, the error function is -1. At x is equal to 0, the error function of x is 0. And at a value of infinity, it goes to 1. So it's kind of got this almost S-shaped like curve. The complementary error function is just 1 minus the error function. And so it looks like this. And so you can imagine that 1 minus -1 is 2. So that's why the error function at negative infinity is 2. 1 minus 0 is 1. So at x is equal to 0, the complementary error function is 1. And then 1 minus 1 is 0. So that's why you get that over there. Okay. You could use either one of these. It's probably easier to use the complementary error function because, as we saw in here, then you don't have to subtract the value from 1. You just use this directly. So that's the solution. Okay. And on your next homework, I might ask you to plot that solution. One application of this equation is to use experimental data to try to determine the dispersion coefficient. The dispersion coefficient is not something that we can enforce ahead of time, and it's not something that we could measure without doing an experiment. And we might want to know that. We might want to know how much mixing there is because it's going to tell us how much of an early breakthrough there'll be in our reservoir. Okay, so recall that this was the solution. Okay, I've written in terms of the error function, not the complementary error function. And what I did last time is I just did some tricks there. I just did some algebra. I multiplied both sides by 2 and moved some things around. I'm interested. What I'm going to do is collect data at the effluent at x is equal to L, or if it was a reservoir, the producer well. And so xd is just 1. X over L is 1. And so yeah, again, I moved some things around. So 1 minus 2 at the concentration at the exit is equal to this. And then you can take the inverse error function of both sides, and you get an equation like this. And so what we said last time is that if you were to plot the inverse error function of 1 minus 2, the dimensionless concentration, versus this 1 minus TD divided by 2 times the square root of TD, that should be a straight line through the origin. And the slope of that line will be the square root of Peckley number. And if you know the Peckley number, then you can calculate the dispersion coefficient. Because you know how fast you injected, you know Ux, you know the length of your core, and you just calculate the Peckley number. You do need the porosity as well. And you may have measured the porosity using techniques you learned in your petrophysics class. So there's a few different ways you can measure porosity. That way, I'm going to mention another way you can estimate porosity, and that is from the data again. So remember, we've got this equation up here. And one thing that we can do is if we say TD is 1, so 1 pore volume injected, and we're looking at the exit, xd is equal to 1, then you get the error function of 1 minus 1 divided by this denominator. 1 minus 1 is 0, so it's 1/2, 1 minus the error function of 0. And if you recall, the error function of 0 is 0, right? If we go back to over here, the error function of 0 is 0, so 1/2, 1 minus 0 is 0.5. What does that mean? That means that when TD is equal to 1, the exit concentration should be 0.5. It should be 50%. What it really should be is 50% of the injected concentration. So what I can do is TD is defined as the volume injected divided by the pore volume, which is UXAT divided by AL phi. I know UX, I know A, I know L, I know how long that took, and that's equal to 1. So what you can do is you can look to see when CD is equal to 0.5 and then determine your porosity phi. Okay, so here are plots of the dimensionless concentration CD versus distance. Okay, and we made some plots about this earlier, but let's say the Peclet number were infinity. What does that mean? It means that it's advection dominated. There's no mixing. You can neglect dispersion altogether, in which case at a particular time TD, and this is at a TD of 0.5, you just have the concentration ahead of the front, the dimensionless concentration is 1, then there's this shock front, and then it's 0 ahead of that. So all that means is, let's see, okay, sorry. So all that means is that the component is traveling with the velocity. So you inject it and it moves at an exactly the same velocity as the fluid is being injected. So after a half of a pore volume, the concentration is 100% the first half and it's 0% the second half. But as you start to add some dispersion, so let's look at a Peclet number of 1,000, which is still a big number, but you start to get some smearing. So what happens is that even before TD is equal to 0.5, or XD is equal to 0.5, the concentration starts to decrease. It's about 0.5, as we said, at there, and then it decreases a little bit. If Peclet number is 100, there's even more smearing. So it almost immediately starts to decrease. And, yeah, so that's here. This is Peclet number is 100. And you can see that at 0.5, we got that value right there. And then you have these lower Peclet numbers, which I probably should have left off because those are not typical values in there, and then that extra term that I mentioned previously starts to become important. But the point is that the shape of this curve changes as the Peclet number decreases. If we looked at the dimensionless concentration versus dimensionless time at the exit, right, and this is something that we can measure in the lab, this is something we measure in the reservoir because we're looking at the concentration in our producer well with time. This is concentration from 0, 1, this is dimensionless time. You can see that for all these Peclet numbers, that at dimensionless time of 1, the exit concentration is 0.5. So that's how, so we use that data. So what we do is we find the time, the real time in days or hours or seconds where the dimensionless concentration is 0.5, and we know that that's equal to a dimensionless time of 1, and we know all the other variables in that equation, so we can calculate the porosity. And of course, you want to make sure that the answer makes sense there. It's going to be between 0 and 1, probably less than 30% or so. But that's what you should get. I'd like to show some real data. So these are some experiments we did in the lab. This is the red points are the data, and then we fit our equation to that. Okay, here's that extra term I mentioned before. We don't have to worry about it, but I went ahead and did that. And you can see that this equation fits that very well. And this corresponds to a Peclet number of 86 or a dimensionless dispersion coefficient of 6. This is for a relatively homogeneous Bentheimer sandstone. There's not that much spreading because it's fairly homogeneous. But as you increase heterogeneity, the dispersion coefficient increases and you get more mixing, more spreading, earlier breakthrough. And in fact, here is a more heterogeneous Silurian dolomite carbonate. And you could see that the breakthrough in this case is more like 0.5, where it was like 0.7 over here, pore volume. So it comes out earlier, and there's some spreading. It's not a perfect fit to the model, but the dimensionless dispersion coefficient is more than 10 times greater than what it was in the homogeneous Bentheimer sandstone. So that's typical. The more heterogeneous your porous medium, the earlier breakthrough you'll get and the more spreading you'll get. Okay, now what does that mean? That means for reservoirs that if you start injecting your component, then it's going to come out earlier. It's going to be earlier breakthrough, and you're going to have worse recovery as well, because what's going to happen is that, let's say you're doing an enhanced oil recovery technique with injected polymer. Well, that polymer is going to find the fastest way possible to get to the producer well. It's going to go, it's a very heterogeneous, so it's going to go through the high permeability streaks, maybe the fractures, and reach the producer well early. And that's not what you want. You want it to kind of do this, you know, as I've described before, this nice moving wall like a piston, and to push everything out. But if you have heterogeneity, that leads to dispersion or mixing, and then you get an earlier breakthrough, which is unfortunate. And we're always looking for new ways to minimize that effect. Okay, I'd like to talk a little bit about mixing zones. So, I mean, what we're talking about with dispersion is there's mixing, which means that there's some spreading of that concentration front. Again, in the upper right-hand corner, I've got our solution for the dimensionless concentration. And we're going to define the mixing zone. This is a little arbitrary, but we're going to define it as the distance delta x in our one-dimensional reservoir in our core at some time TD, where CD is equal to 0.9 and also CD is equal to 0.1. So you're going to have this curve. Maybe I'll go back a few slides. I'll go back to this one. If you look at this one, so CD is equal to 0.9. Let's look at this curve right here. Occurs at XD is about 0.4, and then CD is equal to 0.1. Occurs at about 0.65 or something, right? So what you're looking at is maybe a delta X of 0.25. If the Peclet number were very high, then the delta X would be 0, right? There's not very spreading. This is this nice shock front there. Okay, so delta X, we're looking at the concentration where it's 0.1 and the concentration is equal to 0.9. And that mixing zone, that value of delta X, how much spreading of there, increases with time. So at really early times, you kind of get this nice front where it's pretty sharp, but as time goes on, it starts to spread out more and more and more due to this mixing dispersion phenomena. And so delta X is proportional to T over Peclet number, or since Peclet number is constant, it's proportional to the square root of time. We didn't talk about this, but when we had the 1D water floods, the Buckley-Leverett solution, there was also a mixing zone, and it was proportional to time, not square root of time. So we talked about the analogy between our Buckley-Leverett model for immiscible displacements versus our miscible component transport displacements. They're similar in many ways, but there's some key differences. Here's another difference, is that this mixing zone is proportional to time, where it's proportional to square root of time. So how would I measure that mixing zone? Well, again, what I've shown here is 3 different times. This is the concentration versus distance at different times. And even if you just look at the picture, you can tell that this first curve at early times is a little sharper than at later times. There's more spreading out, and we can quantify that. So we can measure, I did these blue lines here, so when the concentration is 0.9, we can see that the distance is like 0.12 or something. or 0.11. And then when CD is 0.1, I get 0.29, and 0.29 minus 0.11 is 0.18. So the mixing zone is 0.18. Okay, it's 18% of the core length. Now, if we go to a later time, dimensionless time of 0.8, then I can see that CD right here occurs at about 0.64, and when CD is equal to 0.1, it occurs at about 0.95. 0.95 minus 0.64 is 0.31. So this mixing zone, delta x, is bigger than over there. And if we were to plot delta x versus time, we would see that it was proportional to the square root of time. So actually, maybe what we would do is plot delta x versus the square root of time, and we get a nice straight line. Okay, so let me talk about a different kind of tracer test. Okay, by tracer test, what I mean is that we're injecting a fluid into a one-dimensional rock core experiment or a reservoir in the field, and you'll inject this at a certain velocity, and it's just a tracer, so it's usually doesn't affect the flow at all, doesn't react most of the time, and you're looking for it to see when it reaches the producer well. You can do that in the lab, but we do them all the time in the field. Tracer tests are very common at the beginning when you're trying to do a water flood or enhanced oil recovery technique, because it really tells you about how much heterogeneity and mixing you're going to have in your reservoir. And the typical way one way we do it in the lab is that you change the concentration from what it was initially, and when you change and then you keep it that way. So maybe you've got 0 tracer in your rock core, and then you increase it to a constant concentration. Dimensionless concentration is equal to 1, and you keep it that way, and you flow it for a very long time until you get all your data to do that. In the reservoir, that's not particularly practical. And the reason is because that would require a lot of tracer, because we're talking about a big reservoir, and your injection rates, are going to be, maybe thousands of barrels per day. So if you want to do that for many, many days or months, then you're talking a whole lot of barrels of tracer. And these tracers are not particularly cheap, at least the good ones. They have some very good tracers, and they're expensive. So you don't want to be injecting this tracer for days or weeks or months. Instead, what they do is they basically dump in a bunch of tracer over a very short period of time. So they just put in a bunch over minutes or hours or something like that, maybe even less than that. And so I talk about those two different tracer tests here. The first one up here is basically what we've been talking about. So the injected concentration was 0, and then the dimensionless concentration is 1, and you keep it that way. This is the concentration you inject versus time. This is the concentration at the exit or the producer well versus time, and you get this spreading that occurs. Okay? Peckley number was infinity, then this exit concentration would look exactly like what you injected. But it's not. You get this spreading, and so maybe it looks something like this with time. But the other way we could do that is we inject a constant concentration for a small period of time, I'll call it TS, and then you go back to injecting nothing. So you've got this value of 1 for a short period of time, but then it goes back down to 0. Again, if the Peckley number was infinity, then what you would get is that this constant concentration would just move with the velocity. It would all come out over all at once for the short period of time. In reality, what happens is you get this sort of bell curve looking type thing. So some of it comes out early, and I don't really like how I drew that because it's not going to come out at 0. Probably should have come out over here, but it will come out early, and then it'll reach a maximum, and then it'll come down again. So this is what we call a pulse tracer test, and they're more common in reservoirs where we want to not spend too much money on a large amount of tracer. So if we do that, if we inject the pulse concentration for a short period of time, Ts, then what that means is that from 0 to Ts, for that short period of time, the concentration is going to be, we'll call it C2, and we do that at the injector, x is equal to 0. And then C is equal to C1 for, it goes back to what it was before. Maybe that's 0 greater than Ts again at the injector. There is a solution to that. You can use the principle of superposition. We've done this a few times now. We use superposition in Reservoir 1 when we're talking about well testing. We talked about principle of superposition when we were talking about aquifers, and we're using the Van Evergreen and Her solution. Now it's coming back again. And remember, superposition basically just means adding two solutions to each other. It's a mathematical technique that we can solve it. And what you have is you've got a solution for this top part and a solution for the bottom part. And we won't go through all the ugly math, but basically this is what your solution is. So you get this error function, and you get x minus u to t minus ts, and then you get this square root over here, and then you get another error function term over there. And if you put it in dimensionless form, TD and XD and all that, then it looks like this. So TDS is the amount of time that you inject that concentration. Okay, and actually, yeah. So that's what you get. TDS is that dimensionless number of pore volumes of tracer injected. And so what that's going to look like is going to look something like this. But this is the dimensionless concentration versus distance, and these for different Peclet numbers. So remember, if we have a Peclet number that's very high, you don't have very much mixing. So it's almost like you just got this one peak and it moves over there. There's a little bit of mixing because the Peclet number is less than infinity, but you get this little bit of spreading. It's a tall peak, but it's a thin peak. But if you have a Peclet number that's smaller, like 200, then you get some more spreading over here. Likewise, this is the dimensionless concentration, again versus distance. This is for the same Peclet number. In fact, it's probably, well, I don't know if it's maybe, it's probably 1,000. And what you get is this, or maybe it's the 200, I'm not sure, but it's a constant Peclet number nonetheless. And this is at early times, right? TD is 0.1, and you get this. And as you move down, you get more spreading, right? And that's similar to what we were talking about earlier with these mixing zones. As time goes on, it spreads out more and more, and that's what we get. And then if we look at the concentration versus dimensionless time, you'll look at something like this, and if your Peclet number was infinity, everything would come out at a dimensionless time at 1. But a Peclet number of 1,000 is similar to that. It's just this sharper peak. So what you have is you've got a breakthrough time is when the first time you see that tracer come out at your producer well. And so that number is never going to be greater than 1. In fact, for any practical application, it's going to be less than 1. And over here, it looks like, oh, I don't know, it's about 0.8, 0.9, something like that. And then it comes out, and then it continues to come out past a dimensionless time of 1. And it's pretty symmetric here. Peclet number is smaller, then it might look more like this, and it's got an earlier breakthrough time. And then an even smaller Peclet number, so greater dispersion, more mixing, the breakthrough is even less than that. We are going to revisit component mass balance. So if we had a component J, Okay, so J is equal to the component, and I'll use L is equal to the phase. So J could be any component. It could be salt, it could be methane, it could be something else. And L, we could have multiple phases. We could have an aqueous phase, an oleic phase, and a gaseous phase. And what we derived before is we said that the accumulation term, partial respect to T, Cj times porosity, plus Cjs times 1 minus porosity, partial respect to x. The sum over all of our phases, L is equal to 1 to up to 3 phases. And you have the concentration of component J in phase L times the velocity of phase L minus the dispersion coefficient of component J in L times the porosity times the change in concentration of component J in phase L with respect to x. So what is this? This is accumulation. This is advection. And this is dispersion. Okay, so we've seen this before. Just to remind you, Cj is the concentration of our component J in the pore volume, right? And we could have expanded it to include, okay, well, what is it in the aqueous phase, oleic phase, and gaseous phase? But this is the concentration in all the fluids combined. We multiply it by the porosity because we only care about the pore volume. Cjs is the amount of component J that is adsorbed onto the rock surface. So you could have some component that gets deposited on the rock surface and maybe it stays there. And this is on the rock, so it's 1 minus V. We've got our advection term, and we've got our dispersive term. Let's simplify this. Let's look at 2 phases, maybe oil and water, and no dispersion. Okay, now we never have no dispersion, but in many reservoir applications, the Peclet number is very, very large, so it's relatively small. So we'll neglect this term altogether for now. There's only 2 phases, so we can expand that. And maybe we want to expand Cj. So let's do, and we could say that the porosity is constant, V, partial respect to T. Cj is Cjw plus the concentration of component J in the oleic phase times the oleic phase saturation plus Cjs 1 minus phi divided by phi. I pulled out a porosity, so I've got to put that in the denominator there. Plus the velocity u times the partial respect to x. Okay, I'm going to do 2 phases. L is equal to 1 to just 2 now. And that's Cjw times the fractional flow of water plus Cjo times the fractional flow of oil. Okay, so let's think about what I did there. So I had this Cj term, which is the concentration of the entire pore volume. If you go back a few lectures, you'll remember we defined Cj as the sum of the concentrations in each phase times the saturations of each phase. So we've got 2 phases, water and oil. Still have the adsorbed concentration. We pulled out a porosity, so that's why we had to put a porosity in the denominator there. On the right-hand side, we had CJL UL. So C of component J in phase L, so that's like concentration of J in the water phase and concentration of J in the oleic phase. And well, we had the velocity of each phase, but we know that the velocity of each phase is equal to the fractional flow of the phase times the velocity. And because the velocity is constant, I can pull that out. And this is all going to be equal to 0. So I have to check this. I think that I have a sign error somewhere. Maybe there was a negative sign up here that should have been, but I'll have to double check that. But I think that this is right as written over here. We can do some non-dimensionalization. And maybe I'll just go back to defining this Cj as being Cjw SW plus Cjo SO. And this is the concentration of J in the pore volume. I'm going to define Cjs prime. Cjs prime is Cjs times 1 minus phi over phi. And this is going to have units of amount per pore volume. And the reason why I did this is I want this to have the same units as that. So now this is going to be concentration J adsorbed, but it's now also going to be amount per pore volume. That amount might be pounds or kilograms, might be a mass. Then, so this right here is Cj. This right here is going to be Cjs prime. And then I'm going to define this right here as a concentration of advected fluid. I'm going to call it Fj. So F of J is just Cjo times Fo plus Cjw Fw. And this is the concentration of J in advected fluid. We'll also have units of amount per pore volume. Okay, so if I define those three things, then I can rewrite my equation as partial with respect to dimensionless time of Cj plus Cjs prime plus partial of Fj with respect to xd is equal to 0. So what we're doing is we're injecting some component J. It's flowing in one dimension. The concentration is going to change with time and space. You will have some J that gets adsorbed onto the rock surface. This is my advection term. This is my accumulation term. This looks, and you know, I keep on bringing back this analogy, but it looks a lot like the Buckley-Leverett equation for oil and water flow, and we will talk more about that analogy this week.